Now, this is a battery question, and we have here a battery that consists of 10 cells connected in series, and so that means basically that S is equal to 10. Now, if you refer to the formulas that have been provided for batteries, you'll find that when cells are connected in series to form a battery, we can find the total internal resistance of the battery by saying that S multiplied by the total internal resistance of a single cell gives us the internal resistance of the battery. So here we have 10 multiplied by 0.2 ohms, or a total internal resistance of 2 ohms. In addition, we have the total EMF of the battery is equal to S multiplied by the EMF of a single cell, which gives us 10 multiplied by 1.5 volts, or 15 volts for ET. And so now we can draw an equivalent circuit whereby we show the total internal EMF produced as 15 volts, the total internal resistance of the battery as 2 ohms, and we show that there is a 4 ohm load attached externally to the battery. VT then is the terminal voltage of the battery. Now, for part A in this question, we are asked to calculate the current and the voltage across the load, or the terminal voltage of the battery. And so we have a relatively simple series circuit now, where the voltage source is 15 volts and there are 2 series resistors, and so the total resistance of the circuit will be equal to the internal resistance plus the load resistance, 2 ohms plus 4 ohms, for a total resistance of 6 ohms. Now we can apply Ohm's law to calculate the circuit current, whereby we can say that I load equals ET divided by RT, and that gives us 15 volts over 6 ohms, or 2.5 amps as the circuit or load current. Now we are also asked to find the load voltage, and basically there's 2 ways to do that. The easiest way would be to say that the voltage across the load is equal to the terminal voltage of the battery, and that, by Ohm's law, is equal to I load multiplied by R load. We have then 2.5 amps multiplied by the load resistance of 4 ohms, and that gives us 10 volts for VT. Now, in the notes that you have been reading, you'll find that this equation is given for terminal voltage. It is equal to ET subtract the voltage drop across the internal resistance. Now, in this case, this equation has been produced by applying KVL to the circuit, and here the internal resistance voltage drop is equal to the current flows through the circuit multiplied by that resistance value, and we have 2.5 amps multiplied by 2 ohms, and that gives us 5 volts. And so the terminal voltage will be equal to E at 15 volts subtract the voltage drop across the internal resistance of 5 volts, and that again gives us VT is equal to 10 volts. And so 2 ways basically that we can calculate that voltage. Now, part B of this question asks us to consider the information given and calculate the amp hour and watt hour efficiencies. So if we refer to the equations provided in the instructor notes, you'll see that the amp hour efficiency can be calculated as the discharge amp hours divided by the charge amp hours, which will produce a decimal. For efficiency, we multiply by 100% to give us efficiency in percent. And so the discharge amp hours for this case would be 2 amps times 7.5 hours, and the charge amp hours would be 1.5 amps times 13 hours, and that gives us 15 amp hours over 19.5 amp hours, which when we convert to a decimal and multiply by 100 will result in 76.9%. This is the amp hour efficiency. Now for the watt hour efficiency, we again have the discharge watt hours divided by the charging watt hours, and in order to do that, we can take the discharging 15 amp hours and multiply it by the average discharge voltage, which was 12 volts, divide that by the charging amp hours multiplied by the average charging voltage, which was 13.5 volts. Our calculation should yield 180 watt hours divided by 263 watt hours, and that results in a watt hour efficiency of 68.4%.